This video is going to talk about how to draw Bohr-Rutherford diagrams. So at this point you've already learned a little bit about the atom. You've learned about different subatomic particles, so the proton, neutron, and electron, and where they are within the atom. Within this video we're going to learn how to draw diagrams that represent atoms. So if you look at your periodic table, it gives you all kinds of information about a variety of different elements. So what we're going to look at is how do we actually read this information that they've given us for each element. So I've just pulled out calcium right here, and so let's take a look at the information they give us. So this first number up here is what's called the atomic number. So this is element 20. We'll talk a little bit later about what that 20 actually represents, but in this case we'll just call it the atomic number for now. Ca is the symbol for the element calcium. So this here is the name of the element, which is calcium. The last piece on the bottom here is the atomic mass. So in this case, calcium has an atomic mass of 40.078. However, it's important to note that the atomic mass given on the periodic table is the average mass of all isotopes. So an isotope is just a variation of calcium. So obviously there's different forms of calcium that exist. There's not just one kind. Then the different types of calcium's atoms vary based on the number of neutrons that they have. And we'll explore this a little bit later, but the idea here is that this mass represents the average mass of all the different types of calcium isotopes. So the units for this mass would be those units that we talked about last class, which are atomic mass units. Or AMUs. So this is 40.078 AMU. For the purpose of drawing our Bohr-Rutherford diagrams, when we look at these atomic masses on our periodic table, we're always going to round them to the nearest whole number. So what that means is if I was to draw a Bohr-Rutherford diagram for calcium, I would take this number and I would round it to just 40. So a quick review on how we do that. We look at this number right here, which is the number after the decimal. If that number is 5 and lower, we keep it as is. If it's higher than 5, we round up to the next number. So in this case, though, we have a 0 after the decimal, so we keep it at 40 AMU for the atomic mass of calcium. Sometimes, if you look at your periodic table, this is exactly what all your information will look like, but if you look at the one in the textbook, you'll see sometimes these little charges up here. So for calcium, you would see a 2+ in the corner. So that represents the charge of a calcium ion. Now that's a lot of different information that we don't really understand yet, and for this year I've purposely left out the charges because we're going to learn how to figure out what that charge would be based on our Bohr-Rutherford diagram. So there's no charge in your periodic table, and that's done for a reason. So in addition to being given information on the periodic table, sometimes you'll be given information in what's called isotope notation. So let's just take a look at the two different notations that you might see. So this first one right here is pretty easy to read. This tells us obviously that we're talking about calcium. And the number that follows the dash would be the atomic mass. And you'll see why it's important to know the atomic mass later on. If we look down here below, this is a different notation. So these are two different ways that you could see the same information. These two are variations or different isotopes of calcium. So before we go further, let's just define what that means. An isotope is a variation of an element that has the same number of protons, but a different number of neutrons. So these are two different calcium isotopes. So let's take a look at what the information represents. So this first piece down here, notice it's the same in both. That's because this is the atomic number. The atomic number doesn't change. It's always 20, no matter which isotope we're talking about. The number at the top here does change. And that, in this case, is our atomic mass. So here we could be talking about calcium-40, and this one is calcium-57. The difference, again, is that one has a higher atomic mass due to the fact that it has a different number of neutrons. And we're going to make sense of that a little bit later when we start drawing our Bohr-Rutherford diagrams. So again, you could be given just this, which tells you you're talking about calcium with an atomic mass of 40, or you could be given just this, which is calcium with a mass of 57. So before we start drawing our Bohr-Rutherford diagrams, there's a couple important pieces of information that we need to know. And the first one is we're going to look at how do we know how many of each of the subatomic particles there are in an atom. So the number of protons is always equal to the atomic number. Okay, so if you're given an atom, and you know the atomic number, that tells you how many protons you have. The number of neutrons is equal to the difference between the atomic mass and the number. So it's equal to the atomic mass minus or subtract the atomic number. So just keep in mind that this is a subtraction sign here, okay? And since atoms have a neutral charge, the number of electrons must always be equal to the number of protons. So, key word here is when we're talking about atoms. Atoms always have a neutral charge. Later we're going to talk about ions. They're slightly different, but when we talk about atoms, the number of protons is always the same as the number of electrons, so that there's no overall charge. There's an overall charge of 0. So if we have let's say we had 2 protons, which are positively charged, we have to have 2 negative charges to balance that out to give us 0, so which is an overall neutral charge. So next piece here is the steps on how we actually go about drawing our Bohr-Rutherford diagrams. I'm going to refer to these steps as I go through the next few examples. So what I want you to do is just copy down and work through the examples with me, but these steps are here on your handout for you to refer to. Okay? So let's just start by drawing sodium. So notice here it just says sodium, so I'm not given this more complicated isotope notation. I'm just using a normal sodium atom. So to do that, I need to look at the periodic table and find where sodium would be. So if I look here in my periodic table, here it is right here. So if I look at sodium, I can see that it has an atomic number of 11. It has an atomic mass of 22.98. However, we're going to round that to 23. Why 23? Because this is 22.9, so we always have to round up to the next number if this here is higher than 5. So our atomic mass is 23. So let's start drawing the Bohr-Rutherford diagram. So the first step is to actually draw a nucleus in the middle. And inside that nucleus, what we need to do is we need to put the protons and the neutrons, right? So inside the nucleus, that's where protons and neutrons are. So that's the notation there for a proton and a neutron. So P plus is for proton and 0 is for neutron. And if we look back up to our steps, at the top here, the number of protons is equal to the atomic number. So in this case, our atomic number is 11, so we're going to have 11 protons. The number of neutrons is equal to the atomic mass. minus the atomic number. So our number of neutrons is equal to the atomic mass minus the atomic number. So that's going to leave us with 12 neutrons. So far, we're pretty good. We have our nucleus, we have our number of protons and number of neutrons. Next step is to draw the first orbit and begin placing electrons. So remember that around the outside of a nucleus we have these orbits where our electrons are. Just going to redraw that. Okay, well, how many electrons are we going to have? Well, we are going to have the same number of electrons. So the number of electrons is the same as the number of protons. So if we have 11 protons, I'm going to have 11 electrons, and so let's go ahead and start placing those. So the first orbit holds 2. Next orbit holds 8. 1, 2, 3, 4. So notice how I'm going, starting at the top, going clockwise around the circle. Once I've filled each of these positions, I can double them up. So there is 5, 6, 7, 8. Now if I look in total, I have 8 in this shell, plus 2 in this shell, which is 10, but I need 11, so I need to draw another shell. And I'm going to start at the top and just place my last electron. So that's, again, 2 in the middle shell on the first shell, plus 8 in the next shell, which is 10, plus another one here gives me a total of 11 electrons. And that's it. This is the Bohr-Rutherford diagram for sodium. Something to note here is that we talk about, we often refer to this electron here on the very outer shell, okay? And we refer to the electrons in that outer shell as what we call valence electrons. These electrons are important because they help us figure out how a certain atom is going to react. And so often you'll hear me say, how many valence electrons does, for example, sodium have? In this case, it has 1 valence electron. Let's move on to oxygen. So sometimes when I start these, what I'll always do up here is I'll put electrons, neutrons, protons. So before I start, I'm always figuring these things out. Just says oxygen, so we got to go over to the periodic table and find out where oxygen would be. So if I look, oxygen is actually over on this side of my periodic table. And some information on oxygen. It has an atomic number of 8, and it has an atomic mass of 15.99, and we're going to round that, so our 16 will be the atomic mass. So 8 is the atomic number, 16 is the atomic mass. So if we go back here, let's start by figuring out, okay, how many protons do we have? Well, number of protons is equal to the atomic number. So we have 8. The number of neutrons is the atomic mass minus the atomic number, which equals 8. And the number of electrons is the same as the number of protons. So we're going to start by drawing the nucleus. In the center we have our protons and our neutrons. We have 8 protons and 8 neutrons. Draw our energy shells. The first one holds 2 electrons, so I'm going to put 1 and 2. Remember here that I need a total of 8, so I'm going to draw another shell to fit the rest of the electrons. So there's 2, 3, 4, 5, 6. So I've gone around once. I'm going to start to pair them up again. So there's 6, 7, and 8. So that is the Bohr diagram for oxygen. And let me just do a quick count here. This one would have 2, 4, 5, 6 valence electrons. So we would say, we don't need to write this when we draw Bohr diagrams, but sometimes it's good to get in the habit of thinking about it. So this has 6 valence electrons. And those again are the electrons that fall in the outer shell. Okay? So we do not need to write this or highlight the valence electrons. I'm just doing it just to get you in the habit of thinking about it. Okay, they didn't leave us much room here, so I'm just going to take this example over here, and we're going to do lithium next. So again, to start, we're going to do the electrons, neutrons, and protons. So let's go find lithium on the periodic table. Here it is right here. We have an atomic number of 3 and an atomic mass of 6.9, so we're going to round that to 7. So we have an atomic mass of 7. So our protons are going to be the same as the atomic number, and our number of electrons is the same as the number of protons, and our neutrons, that's going to be our atomic mass minus the atomic number, so we are going to get 4. Start by drawing our nucleus. Nucleus has our protons and our neutrons. We get 3 protons, 4 neutrons, and then we need to just draw our energy shell. I hope your diagrams are a little bit neater than mine, given that you're not drawing on a computer. So let's place the electrons, 1, 2. Only can put 2 in the first cell, so I need a second shell to put my third electron. So lithium has 1 valence electron, and there's the Bohr diagram for lithium. Last example here, we're going to do calcium. Again, I'm just going to move it over here, but since I'm tight on space. Let's go find calcium on the periodic table. Here it is here. So in this case, we have an atomic number of 20, atomic mass of 40. So our atomic mass is 40.0, so we would leave the atomic mass as just 40. So protons, same as the atomic number. So in this case, 20. Number of electrons, same as the number of protons, and our number of neutrons is our atomic mass minus the atomic number, which gives us 20. Okay. So if we look back here, we have an atomic mass of 40, atomic number of 20. Subtract those two, and we get 20 neutrons. Start by putting our protons and neutrons inside the nucleus, and we have 20 protons and 20 neutrons. Start placing my electrons. 2 in the first shell. I'm going to cheat a little bit here and use a pre-made circle. I'm going to need a few energy shells, so I'm just going to put a couple here. So 2 electrons in the first shell, 8 in the second. So now I have a total of 10. I can keep going because I need a total of 20. There's 18. I'm going to put in one more circle, so one more orbit. So there's 2 plus 8 gives me 10, plus another 8 is 18, 19, and 20. So calcium's a bit bigger when it comes to drawing the Bohr-Rutherford diagram. But if we look at it, it actually has 2 valence electrons here. So lots of energy, lots of different orbits or energy shells, but only 2 valence electrons. So at this point, what I would like you to do is actually pause the video and try these next few diagrams on your own. So hopefully you've had a chance to try these on your own. We're going to go ahead and take them up now. I put a couple things here just to speed up the process a little bit so I don't have to draw everything. So we're doing chlorine, so let's go look at chlorine on the periodic table. So chlorine is over here on the right side. We have atomic number 17 and atomic mass 35. So our number of protons will be the same as the atomic number. So one more time, our atomic number of chlorine is 17. Number of electrons is the same as the number of protons, and the number of neutrons is the atomic mass minus the atomic number, which is going to give us 18. So if we go over back to the diagram, I have my red nucleus here, and my protons will be 17. Neutrons will be 18, and I can start placing my electrons, 2 in the first shell. And I need to keep drawing more shells. I'm going to put a few in because I know that I'll need them, so just bear with me here. So there's 2 in the first shell and 8 in the second. Now I've put a total of 10 electrons, and then I'm going to put the last 7. And there's chlorine. Now if we look at, oops, I put 1 too many electrons there. I only need 7 electrons, or 7 valence electrons in chlorine. So that's why my last shell only has 7 instead of all 8. So there we go. There is chlorine. Next one is potassium. We need to find that on the periodic table. So here's potassium right here. We have atomic number of 19, and we have 39 as the atomic mass. Protons are the same as the atomic mass. Number of neutrons is going to be, or number of electrons is the same as the number of protons, and the number of neutrons will be our atomic mass, which is 39. Subtract our number of, atomic mass, subtract atomic number. So my nucleus, I have 19 protons, 20 neutrons. Start filling my energy shells. So starting with the first one, there's 2 electrons. Now I've placed a total of 10. $18. I still need 1 more, so I'm going to put on another energy level. And there's the last electron. So potassium also, similar to some of the ones we've drawn earlier, has 1 valence electron. So that's a total of 19 electrons, 19 protons, and 20 neutrons. Okay, so for sake of time, I've done the next 2 solutions for you already. So here's beryllium, 4 protons, 6 neutrons, and 4 electrons. Magnesium, 12 protons, 12 neutrons, and 12 electrons. There it is right there. We have 2 in the first shell, 8 in the next shell, so that's a total of 10, and then 2 valence electrons in the final shell to give us a total of 12. Same thing as before, we're going to need to know the number of protons, neutrons, and electrons. So carbon on the periodic table is atomic number 6. So we know that no matter what, we're going to have 6 electrons. What's different about isotopes is that this number right here, remember, tells us the atomic mass. So in this case, we have 6 electrons and 6 protons. That's normal. What will change in this case is that our atomic mass is 12. So our neutrons will be 12 minus 6. So the atomic mass minus the atomic number, which gives us 6. So carbon 12 will look like this. There's our nucleus, and then we're going to start drawing our energy shells. There's the first one. And then the second one, now we can place our electrons. And there's 6 electrons. So again, this number beside it tells us the atomic mass. So if we look over at the next one, we have boron 10. Notice that if we look at boron on the periodic table, it has an atomic number of 5. If we were to just take this mass right here, this mass would actually give us, this mass would actually be rounded to 11. But since we are given the isotope notation, the mass that we are using for this specific isotope is 10. So we're going to actually use this as their atomic mass. Protons and electrons. So 5 protons because the atomic number is 5, which means we have 5 electrons. Number of neutrons will be 10 subtract 5. And let's draw our element. And there's 5 electrons. So again, the process is actually very similar to the way that we would do a normal Bohr-Rutherford. The only thing we have to pay attention to is the atomic mass. That's what's changing between the different isotopes, okay? So the final two, again, same thing. They're isotope notation, but just written in a slightly different way. So this one's great because we don't even have to look at the periodic table. There's the atomic number. There's the atomic mass. So if we set up our number of protons, neutrons, and electrons, our atomic number will tell us the protons and electrons. And our number of neutrons will be the atomic mass, subtract the atomic number. So in this case, we're going to get 8. Now we can draw our Bohr-Rutherford. Two electrons in the first shell, and then I can fill the rest in to the other shell. 3, 4, 5, 6, and 7 electrons. So there we go. There's this specific isotope of nitrogen. So notice that we were doing the Bohr-Rutherford for an isotope of nitrogen that has a mass of 15. If we look on the periodic table, the average atomic mass is actually 14, and that's because there's slightly a few different types of nitrogen, each with a different mass, and so this number here again is the average of those different masses. And the reason that we use the isotope notation is because we're drawing a very specific isotope. Keep in mind that if you're not given isotope notation, you're just going to use the average atomic mass that's given on the periodic table. And finally, we're looking at, this time, we're doing a sulfur atom, and this gives us all the information we need. So there's atomic number and atomic mass. Atomic number tells us the protons and electrons, and neutrons will be our atomic mass minus the atomic number. So we have a total of 20 neutrons. Start placing my electrons. The first shell will have 2. Next shell will have up to 8. So there's a total of 10, so we need to keep going. There's 11, 12, 13, 14, 15, and 16. So there's the isotope of sulfur that we're talking about. And that's it for Bohr-Rutherford diagrams.